Hi folks, now we're going to talk about solar power and where it comes from. So the first thing I would normally do with a face-to-face class is ask them this question. This is something that you should be able to do as well. How much power does the sun produce? This is something that we would calculate here from Earth. We know that the sun is putting out lots of heat and light, and we can measure that which hits the Earth's surface, and that which, there's going to be more of it that hits the upper reaches of the atmosphere. Remember, the Earth has a atmosphere, and some of the energy gets reflected away, and some of it gets absorbed. So if you take, say, a solar panel, it's a meter square, and measure how much output power you get on the ground, then you're not going to get the same value as what you would get at the top of the atmosphere. So at the top of the atmosphere, you get about 1400 watts per square meter. And given that the Earth is 150 million kilometers away from the sun, and that the radiation from the sun is going to hit every single square meter in that sphere, then you could calculate how much output power the sun is putting out. And you'd get somewhere around, using these formulas, you would get around 4 times 10 to the 27, I believe, watts at any particular moment in time. Oh yeah, I got the number right. So that's quite a lot of power. And all this is determined just by calculating how much you receive here on Earth. Now, this is equivalent to taking a nuclear power plant and combining, a bunch of these power plants together, the yearly output, and putting it into every second. There's roughly 31 million seconds to a year. So you don't really get a one-to-one correspondence here, because you're putting the yearly output power of 2.5 billion of these nuclear power plants, the yearly output, and you're compressing it into 1 second. Basically, to be a little bit more honest about the thing, consider that a nuclear power plant basically consumes about the same amount of space as, say, a community college. So say roughly a square mile, maybe less, but within a factor of 2 or 3 you got the right answer. Now consider how many planets you're going to have to put those nuclear power plants on to equivalence the amount of power that the sun is putting out. I think the order is like about 6,000 Earths you're going to need. Powers of 10 really can be kind of scary stuff, but it's the easiest way to deal with that thing. So there's no way that uranium could actually power something like the sun. But we're going to take a look at it. One of the other things early on that people did is when they discovered new power sources, they basically asked the question, well, could the sun be made out of that? And this is an example that I would have my face-to-face students do, is basically consider gasoline, basically using hydrocarbons to drive the sun. And when you do that, you would come up with a number that, given the amount of mass that you have in the sun that you can measure, right, using Newton's law of gravity, and the radius of the Earth and how long it takes the Earth to go around, blah, blah, blah. You find out the mass of the Earth, and if you assume that all that mass is gasoline and you consumed it, not even considering that you need oxygen to consume it with, but assuming that all that was gasoline and you converted it, then you could ask the question, well, given the amount of power that we're receiving from the sun, how long would the sun last? And if you do that, then you find out that the sun would last roughly 5,000 years. A lot less than recorded history. I mean, that goes back 6,000 years, easily. If you go back to the Egyptians, you go closer to, 8,000 years. So, all in all, they should have seen some sort of change, as well as we should have by this time. All right, now another possibility is from gravitational heating. We understand that Saturn and Jupiter are both still compressing. Jupiter is compressing, getting smaller, and that's why we think it's radiating twice as much energy as it receives from the sun. And Saturn is differentiating. The helium hydrogen is raining through the helium, so denser things are falling through, coming to the core, and lighter things are rising. So that gives rise to more heat as well. And so given the current rate of energy production of the sun and gravitational heating from the mass that's still compressing, then we would say that would last 100 million years of life. And this doesn't agree with radioactivity. Okay, but there are some that say that radioactivity is bogus anyway. All right, well, that's nuclear physics, and basically a not understanding of the basic structure of nature. So let's continue. So we've canceled off two of the four forces, and now we're left with the strong and the weak nuclear forces. And both of those have an aspect on the problem. So let's remind ourselves what these two forces are. Let's remember what the nucleus is consistent of. A nucleus contains protons and neutrons, and we recalled earlier that neutrons are there in a nucleus to make sure that the protons, which are electromagnetically a single charge, positive charge, that these guys don't get away. Namely, that the nucleus doesn't split apart, because like charges will split things apart. So the the neutrons are there to act as a glue to keep the nucleus in one piece. And we know that's got to be the case because we have nuclei that contain multiple protons. So this theory works pretty well. All right, so in a little bit more detail, the nuclear force has this type of attractive potential down here, and the Coulomb force is repellent up here. So basically what ends up happening is if a proton approaches a nucleus, then it's going to be repelled unless it has enough energy to overcome this barrier, and then it's going to be suddenly attractive. Okay, so in order for that to happen, you have to have lots and lots of energy. Okay, so there are essentially two ways of getting energy from the strong force. As you know, there's fission and fusion. And let's first take a little step back and remember the fission part of this problem. There is a link here, and let's see if it operates. Okay, so let's continue. This is a link that I like, and we'll get to it. I don't know if... I'll skip the ad now. And this one will last only about 4 minutes. One of the things I'd like you to consider is that any government that has tried to make a nuclear weapon has. It's essentially pretty simple to do. The physics is not too tough. The engineering is, and that's the easiest way to find out if governments are trying to produce nuclear weapons. Now, that Tsar bomb, Sakharov, a Russian nuclear scientist, was so appalled by how much nuclear fallout occurred that the Nuclear Test Ban Treaty was negotiated and signed not too much later. So a lot of the testing since '61, especially for the Soviets and the US, was underground. Okay, so let's get back to our topic of interest, which is the sun and how it produces energy. Alright, so fission is this process which we've just looked at with nuclear weapons. Although there are hydrogen bombs and things like that as well. But fission is where we have heavy nuclei getting bombarded by a neutron or some like particle, and the energy is released by the splitting up of the atom into two bits. Okay, and what ends up happening is you create a chain reaction because more neutrons are created than you start with, and these guys can then run into other uranium nuclei, for example, and then split apart. Okay, so fission is what causes our nuclear power plants to work and the atomic bombs. Take a look at how many terajoules are created in such an instance. And so these are hard numbers to sort of think about, but a terajoule or 4 terajoules is about a kiloton of TNT. So now we're going to go with 55 terajoules, and then we're going to go to hydrogen weapons where it's even more so. Okay, but there is a problem though. As you can see by our chemical abundance in the sun, there's no uranium to be seen. So there's no source of fuel for the sun to fission apart and create energy that way. Fusion is the other possibility. We take 2 protons and we force them together. We discussed this before, and this is a multi-step process, and basically what we end up finding out is that through these drawings, at low energies, the 2 protons come together and they just glance away. But at high temperatures, when these guys are going very, very quickly, they can get very, very close and then they're able to stick. Okay, so that's the basic idea. Fusion is very difficult to make work on the ground, but in the sun, conditions are perfect. Okay, so remember we were talking about 55 terajoules for an atomic bomb. For a hydrogen bomb, we're talking about not 55, but we're talking about 210,000 terajoules. So let's see, what we're talking about is what, 4,000 times more power there? So we need to have, in order to make this work, we need to have a lot of hot, free protons floating around. We need to have high pressures, and the sun's got that in abundance. Remember, the core of the sun, we think, is about 150 times the density of water, and the temperatures in here are about 15 million degrees Kelvin. So things are moving very, very quickly, and the densities are very, very good. So in order to create this luminosity, how much energy are we producing? 2 billion bombs per second. 2 billion hydrogen bombs per second. Tremendous amount of power. The scale of it is unbelievable. 600 million tons of hydrogen are being burned, if you want to use that word, every second. But get this, 4 million tons of material disappears per second. Disappears. The sun is getting lighter every second by 4 million tons. I wonder if that's about the size of the Earth. I'm forgetting how many tons are in Earth's mass, but that's something for you guys to think about. How many Earths is disappearing from the sun every second because of the amount of light and heat and power that we're receiving from it? Okay, so we've seen this problem before, and basically the idea is that in order to maintain this energy product, we can figure out how long the sun will live in this regard. And what we'll come up with is that if we consume the entire sun, then it would last 100 billion years. And I have spoken before is that we expect the lifetime of the sun to last only about 10 billion. The difference between the two numbers, a factor of 10, is due to the idea as this, that only the core is cycling around materials around such that only the core is being consumed, and then the outer portions of the sun, the radiative zone, the convective zone, the photosphere, and that sort of thing, they will not contribute to the output power that we see in the sun. So when the core gets used up, it's going to, that core is going to change into helium, and then the sun goes inert. Now, if you take the stars and galaxies class, then you'll find out that there is another process that will happen. The sun will go to a red giant phase, and helium will be consumed and turned into essentially carbon. Okay, so let's continue. We have strong and weak nuclear forces taking effect here. And basically what I want to show you is the process that is occurring most frequently in the sun, the hydrogen getting converted into helium straight away. It's called the 6-proton method. Okay, so but first we need to consider antimatter, because that will come into play in our consideration. Antimatter in the terms of a positive electron, a positron, and when these two beasties come together, then they create energy in the form of a gamma ray. They annihilate. So just like on Star Trek. Okay, so this is the proton-proton chain. Hopefully you're a visual learner as I am, and see this for what it is. We start off, remember, we have a plasma going on. We have protons and electrons just floating around. They're not in any atomic connection whatsoever, so we just have protons in a soup, and in that soup we have electrons. So we have two protons that come together. One changes state into a neutron. They stick together, forming deuterium. And because it changes state, we have to maintain charge conservation. And when we do that, we create a positive electron. So a positron gets formed. And then also another thing has to be created called a neutrino. Neutrinos are very light mass. Mass was just discovered not too long ago, about year 2000 or thereabouts. And it carries off some amount of energy. This neutrino does not interact very strongly with anything and just immediately goes through the sun. It takes only a few seconds to go through the entire sun. While any photons that are getting created, like this one over here, will take on the order of 500,000 years to get through the sun. All right, so two hydrogen nuclei come together, form deuterium nucleus. This deuterium nucleus combines with another hydrogen proton, creates helium-3. This helium-3 is excited and it releases a gamma ray. This positron immediately converts with another electron, remember it's in the soup, and creates photons which then propagate away. Okay, this helium-3 combines with a helium-3 from this chain down below that's occurring at the same frequency as these guys are. They combine together to create helium-4, and part of the helium-4 process, or the two helium-3s coming together, part of the process is not only do we create the helium-4, but two protons pop out. So the net, or the gross, is 6 protons come together. 1, 2, 3, 4, 5, 6. 6 protons come together. They produce 2 positrons, 2 neutrinos, 2 photons, and 2 hydrogen nuclei, as well as a helium nucleus. The net result is 4 protons going to into a helium-4 nucleus, along with a bunch of photons and a couple of neutrinos. Okay, so the sun is losing energy all the time. The nuclear reactions are the possible source. 4 hydrogen nuclei turn into 1 helium nucleus. Remember, the helium nucleus is smaller than the 4 hydrogen nuclei, so the sun's core is actually shrinking a little bit, and the lost mass becomes energy. Very curious that way. Okay, so naturally this whole thing is a little bit more complicated, and there is another, the sun is mostly converting hydrogen into helium in this fashion, although there is another process that converts 4 protons into a helium nucleus by using carbon as a go-between. The hydrogen combines with the proton, converts into oxygen, then it goes to nitrogen, and then returns back again. That's called the CNO process. Okay, so to summarize, we basically got something that looks like this, and we get fusion out of it. As I mentioned before, if we have photons that are being generated in here from the helium-3 production, or the initial production of deuterium creating that positron annihilating with an electron, photons will take about 500,000 to 1,000,000 years to get out. It's sort of a random walk process, and neutrinos, on the other hand, come zipping right through. 2 seconds later and they're out. Remember we were talking about 2 billion hydrogen weapons going off at any second? Well, what is keeping all of that from just the sun blowing apart? Well, the process that we have to consider here is what is called hydrostatic equilibrium. The pressure caused by the 2 billion hydrogen weapons going off is causing a little parcel of gas to expand, but we have all the mass of the sun pressing down on it. So these two forces balance each other out and give rise to a stable situation. There is another set of forces that are also in equilibrium. That is one that's called thermodynamic equilibrium, thereby where if you have too hot of a temperature, then the rate at which hydrogen gets converted into helium increases. And since you have a higher temperature, then the sun will get bigger. As the sun gets bigger, then the energy on an infinitesimal surface gets less than, so it cools off. So you have this balancing that if there's too fast of a rate of hydrogen being converted into helium, then the sun expands, it cools off, and therefore the sun decreases in size again. The decreasing in size increases the temperature, which causes, so there's a feedback loop there. Just like the hydrostatic equilibrium, we have a thermodynamic equilibrium there. Now these things fall apart though if if we don't have fusion occurring in the core, and that we'll see in the next Stars and Galaxies lectures on evolution of stars. Okay, so this is our basic model, and now we can estimate such things as pressure and density and temperature for our sun at the core, and then see what happens when it comes to the outside, and then compare our measurements with of the outside surface with that from our model. And we find that it works pretty well. Some things didn't work extremely well in the beginning, and that was the amount of neutrinos we were expecting would be 3 times what we really found. That was what was called the solar neutrino problem, but we'll talk about that in just a moment. The first one is this idea called helioseismology. Because of all these explosions going on, the sun vibrates. Think of the Earth when an earthquake happens. Okay, the whole planet vibrates a little bit. And we can detect the earthquakes from all over the Earth. Well, we can do the same thing for the sun. And here's a picture of this sort of situation. The blue regions are where the gas is expanding outwards, and the red regions are where we have expansion inwards. But the idea is this. If you do a Fourier analysis of the outside surface, then this is a representation of what's going on the inside. So I don't need to understand specifically what's going on the inside, what kind of noise is being created. All I have to do is look at this thing and project back inside, and I get a very good idea of what's going on. It's like taking a look at the top of a drum set and noticing its vibrations, and then from those vibrations I can predict what kind of activity the drummer is doing on the surface in order to create those sounds. Okay, that's I just can predict that, and then I can compare that to what is actually happening. Okay, and the same thing is true with this. Okay, so the second test is the solar neutrinos, and as we pointed out before, the solar neutrinos are being produced in the very core, and they pass right through the sun, and most of them go through the Earth, but we can intercept some of them and determine how many are being created, and actually 2/3 were being lost, and that was, as I said before, caused physicists to it was a real pain. And this problem was solved in 2001, and it did get a Nobel Prize. And I was lucky enough to hear Hans Bethe talk about the solar neutrino problem back in 1987 or thereabouts. This person is the most intelligent person I've ever seen. A little sidelight on that: I've been in the presence of him and of Hawking, and the comparison between the two to me was no comparison. Maybe because I could understand Hans Bethe better, even though with his thick accent. But at any rate, the idea of the solar neutrino problem was figured out, and now it isn't a problem, sort of. Until recently, as I indicated here, we're only observing the high energy neutrinos. These are the ones that we want to observe. These are the ones I'm talking about, that the two protons come together and they form deuterium, the positron and the neutrino. And it's from these guys that we really want to detect the neutrinos from, and we can't yet. We're detecting neutrinos from all sorts of other processes, as indicated by these red guys here. And this will give you a picture of what we would want to observe as opposed to what we are observing. And these are the detectors that we actually have in operation that are detecting anything. I'm not exactly sure what these two guys are, other than chlorine-37 and gallium-71 have detective abilities down in this regime or up in this one. But be that as it may, we're observing neutrinos at much lower rates than what we would want, because they're too low in energy to observe. So we have to make approximations from our theories, basically getting us back from these small numbers to this big one. It's sort of like when you're talking about a dog and the tail wagging the dog rather than the dog wagging the tail. Okay, another representation of this picture is, we're measuring these guys out here, and what we want to do is measure these guys in here. All right, now a new problem has surfaced back in 2015. I suppose I'm touting myself and trying to keep up to date. This new problem has to do with helioseismology, and given, as I said before, helioseismology allows us to determine what's inside. This is allowing us to figure out what is the metal content of the sun. Metals for an astronomer is anything other than hydrogen and helium. So if density changes, then that's going to cause sound waves to travel differently in the sun, which is going to give rise to, raised parts of the sun and lowered parts of the sun. And our models are indicating that the metallicity is not what we'd expect. Okay, these are the two numbers here, 0.7 versus 0.2, and look at the error bars on this stuff. It's tremendous what the error bars are, and they don't agree. It sort of is similar to what we were talking about with the gravitational constant. People are coming up with two different measurements that are totally different from each other. Maybe it's, as indicated here, maybe it's an indication of new physics. At any rate, helioseismology is a very interesting field, and people are working on it and applying it to other stars out there. If we apply it to other stars, then this becomes another technique to determine mass, radius, and age to these types of accuracies to stars that are nowhere close to us. Well, they're sort of close to us, but the nearest star is like 5 parsecs, 3 parsecs away. So without seeing it, we can determine its mass, its size, and its age. And remember, I don't know distances to, about 10% accuracy anyway. So if I can get anything better than 10% accuracy on anything astronomical, I'm really a happy camper. Anyway, another really interesting way of figuring out what's around us. Tremendous what's going on. Science doesn't stand still. Okay, so here's another picture of the helioseismology of people looking at other things, and the citation, if you're interested, is Physics Today, volume 68, number 5, page 36, and that's from 2015. Okay, so some more details on helioseismology if you're so inclined to take a look at these things. Okay, thank you very much.